So first of all, I hope everyone's having a marvelous time with the symposium. I'm sorry I haven't been able to be around. I'm sure the previous presentations have been marvelous as well. So my name is Sarp Kargı. I'm a physics student at Boğaziçi University. And today I'm here to talk to you about how to use methods from statistical mechanics in order to analyze complex networks. If you have bothered to read that very long paragraph that is my abstract, you will have noticed that I touched many topics in there, and I hope to touch them in my report. However, due to the time constraints of this presentation, I will be focusing mainly on how to utilize the Ising model in order to accomplish our goal. So, first of all, let's have a very brief introduction to what networks are. I'm sure many of you have at least some surface familiarity with it, but very simply, we can describe networks as a set of vertices that are connected by edges, and each such configuration, each such construction has its own probability to be. And the main difference of networks from graphs is that vertices and edges of networks can have various attributes that I won't touch here, but these attributes can be used to let these networks model some real-life systems, such as brain networks, neural networks, social networks, and all that stuff. And one important property is that edges can be weighted and directed. We won't see many examples in this presentation, but for some models, there is importance in that weight and directedness. So one property that I would like to highlight while we're in this slide is that this concept of a cycle in which from one vertex to another, there's more than one path. Because now we will see the antithesis of it, which would be a tree network in which there is no cycle and any two vertices are connected only via a single path. And even if a network is not completely a tree network, it can be a tree-like network where any existing such cycles are very large, even infinite, such that you cannot easily reach a dividing path, easily reach the first vertex, and locally this network would converge to a tree. And mainly in our modeling, we will be interested in these tree-like networks. This is important because for some behavior of these statistical models, infinite cycles are necessary in order to explain some behavior. And these are two major examples of tree-like networks. A Cayley tree is a finite tree network, as you can see, and a beta lattice is an infinite expansion of a Cayley tree. And there is this one concept I should have included as a writing in my presentation of a thermodynamic limit of such a system, where the number of these vertices will go to infinite, which if we took a Cayley tree to its thermodynamic limit, for example, we would obtain a beta lattice. So we talked about networks generally. Then what are complex networks? The important property to explain complex networks is the sense of Q, a degree. It's called a degree, which is the number of vertices that are nearest neighbors of a given vertex. So, for example, for this Cayley tree, for each vertex, the number of nearest neighbors would be 3. 3 and 3, I don't know why, looks like that. And P of Qi would be the probability distribution of having degree Q at vertex I. What defines a complex network is the fact that this probability distribution is not simple, such as a Poisson distribution, a Gaussian distribution, etc. So it can have very complex configurations, and therefore usual mathematical models can get really complex in explaining complex networks. So why do we even try to use statistical mechanics? Why do we even try to do physics on these mathematical structures? Well, statistical mechanics, I absolutely don't have time to delve into any of the history, but it's a very well established framework for explaining large scale behavior of a system, and also can well explain interfaces between large systems, such as large tree-like networks. And there's a very important framework, framework that is called a phase transition. And this phase transition can be well utilized to explain some behavior of interest for networks, such as percolation events, synchronization events, which I hope to go into detail in my report. So we have come to the meat of my presentation, which is the Ising model. An Ising model consists on either up or down spins, a configuration of two different spins on a lattice. And I should absolutely have drawn a lattice here. I'm sorry about that. But this spin configuration is determined by this Hamiltonian term. The Hamiltonian term is a determinant of the energy of the system. And the minimization of this Hamiltonian term gives us the properties of the system. And here we have a interaction coupling between two vertices, Jij, and a adjacency matrix, Aij. And especially this Aij term is what encodes network topology. This looks like a very simple term here, but you can have all sorts of fun with it, which I won't have, unfortunately, here. But yeah. So the first kind of method to use here would be a mean field approach, because we know from previous theory that a mean field theory is exact for any Ising model on lattice for dimensions bigger than 4. And complex networks can have dimensions much higher than that. And again, this is not something I can delve into here, but it has been found through analysis that this kind of approach is qualitatively valid for a small world network. It can describe behavior, phase transition behavior, etc. However, for a scale-free network, such as a Barabasi-Albert network, at thermodynamic limit, this, for a scale-free system, it is ordered at a finite t. So the critical temperature for which the phase transition will occur goes to infinity. And this is not at all what the mean field theory says. And there's a question of why here. And this, it turns out, due to the strong heterogeneity of network, the strong variations and fluctuations of degree probabilities between different vertices. So there are three main methods that we will explore in order to utilize this Ising model on networks, which is the beta-Pyles approximation, belief propagation algorithm, and an annealed network approach. So the beta-Pyles approximation. For the beta-Pyles approximation, the Ising model Hamiltonian is defined only for a central cluster rather than all nodes in the network. And we have, for a central cluster, we have a central node I, for example, and the fields for the neighbors are averaged based on a cavity method, as we will see here. So we can define this cluster of black nodes. At the center, we have the node I. And for example, for the node J, we have such a field coming from its own neighbors called the cavity field, this phi Ji term. So this is the Hamiltonian for that cluster. We have our coupling between I and J. We have a local magnetic field defined for the vertex I, and then the cavity field at J times the spin of J. And for the total field at I, we can also define it as the field at I itself, and then all of the influences from it, the central node's neighboring vertices. And this is a mathematical description. I can't go too much much into it. But through some derivation, we can end up with a relation that brings together the cavity fields and these incoming influences. There is a switching of what do you call indices here because of the details of derivation, but while I can't do that here, they are not very difficult to figure out. So, if we apply this beta parallels approximation at a regular beta lattice, that is, we have a uniform magnetic field H, we have constant coordination number, constant degree Q, we have homogeneous vertices and edges, we reach this given result for the magnetization, which is nice, which is very cool. We have figured out at least some sort of network using a beta parallels approximation. I hope this is sensible. I know I'm fast with the details. Unfortunately, I kind of have to be, but again, I will go into more detail in the report and there will be much more full derivation. So we can determine the critical temperature in which a phase transition will occur, and for very high coordination or very high degree, we have we approach mean field theory behavior anyway. So that was it for the beta parallels approximation. I think I'm okay. So we have next belief propagation algorithm. This is a little detailed. To be quick about it, we can define this new term for the probability of vertex I to have some spin up or down, as is our Ising model. And then what we do for the belief propagation algorithm, we start with some non-equilibrium prediction, and then we have incoming messages as defined in this framework from neighboring vertices. And when we bring together these incoming influences at J, incoming messages to I, then we can define an updated version of our initial prediction, which we hope after some iterations will converge into a fixed result, equilibrium result for our spin distribution, which ends up equivalent to the recursion relations of beta parallels approximation. And lastly, we have an annealed network approach, where instead of relying on the complex topology of our network, we try to replace it with a fully connected weighted graph. A fully connected graph is one in which all vertices are connected to all others, and this brings a result that is a bit closer to mean field theory, but also can account for network heterogeneity because it is a weighted graph, and it is a good approximation in critical region. So this is how we define our adjacency matrix using measures of degrees for I and J and the average degree. And eventually, after having our Hamiltonian defined, we can derive a magnetization using Thouless-Anderson-Palmer equations. I had hoped to introduce these exact equations for fully connected graphs, but I realized I would absolutely be unable to come to that spot in this presentation. And again, our critical phase transition is defined with Q squared average and Q averaged, and it approaches an exact uncorrelated network solution for Q squared averaged. Uncorrelated networks, by the way, are networks where the probable degree distribution between two vertices are absolutely unrelated. It is random distribution. So two details I end up writing here. The annealed network is inaccurate for this term going to 1, in which is called the percolation point, because when it is, I think, lower, when this measure is lower than that, percolation does not occur. We cannot get a spin region, ferromagnetic spin region. And also the annealed network predicts some non-zero critical temperature, which is not in agreement with the exact model for fully connected graphs. So first of all, how am I for time? 3 minutes. Oh, it turns out I ended up being too fast, and I could have gone into much more detail. I apologize for that, but I think it's still a good point to start approaching the end of my presentation. So this ends up just a teaser for how we can use this Ising model to explain some network topologies, such as a regular tree and a correlated network. We also have so-called small word networks and growing networks. And finally, again, in my report, I go a little bit into how spin glass configurations arise from these models. Lastly, I have 2 more models to briefly introduce as other methods from statistical mechanics that are used to analyze networks. The first of which is, as you can see, the POTS model. This, instead of having just an up or down spin state, generalizes it into a p number of states where spin could, for example, end up at an angle all the way to down. And here, this delta term gives us that if the 2 spins are parallel, that term will be 1, there will be an interaction, and if they are not parallel, this interaction ends up 0. And the other model is the so-called XY model, which describes planar rotators, which describe continuous configurations for our vertices. So it brings us a continuous symmetry, unlike the Ising model and POTS model. And I'm afraid that's it for my presentation. I hope it was fruitful and you enjoyed your time. Thank you. So, any questions?
So I'm hopefully you are ready in this topic, but go to the message 5 slides back, I think.